All right, welcome to chapter 6. Starting off here, we're going to go back to some of our function notation here. We're going to talk about some special functions called composite functions or composition functions. Given the two functions f and g, the composite functions denoted by f, a little circle, and g. It's not the word fog. You read this as f composed with g or f of g. I kind of prefer f of g. All right, now there's lots of different ways also to write it besides that f circle g. You can write it as f composed with g in parentheses of the x or f of g of x. And this is the notation I prefer because it really depicts the whole definition of this composition function. Composition functions are functions inside of functions, which means you've done this before. When you simplified expressions by orders of operations, you were always told to simplify inside the parentheses first. And then you go and simplify everything on the outside with that new value that you created from the inside of the parentheses. Same concept. So here you simplify the inner function first. You take that answer you get from g of x, and that number, you plug it into the f of x function. So you're going to do 2, substitute and simplifies. Now, the domain of f of g is the set of all numbers x in the domain of g, such that g of x, that's the y-coordinate, such that the y-coordinate of g is in the domain of f. So the y-coordinate becomes the x-coordinate for the f function. So here's kind of a flow chart. X goes into the g of x function, that's the input. Output is y of g. But then that value becomes the input of the outer function f of x, and then the output, you get a new y-coordinate. All right. Now, it's important to understand that with these domains of this g function being the inner one, you could have restrictions from the g function that have to go through to the f function. So I'm starting out with ugly functions right away. You've probably seen these before, those ugly fractions before. So if I had f of x equals 1 over x plus 3, I have a domain restriction. G of x, 4 over x minus 1, there's a domain restriction. X can't be equal to 1. So if I'm going to ask you to find the domain of f of g, that means g of x is the inner function. That means this domain restriction definitely goes with it. That's there no matter what, because that's the x you start with the inner function. Now here comes the tricky part. The second part is your outer function has a domain restriction. X can't be equal to negative 3. So you have to guarantee that the whole entire g of x function is never going to be equal to that negative 3. So we take the 4 over x minus 1, set it not equal to negative 3, and then we're going to solve this. So we'll multiply the x minus 1 to both sides, cancel it on the left, distribute the negative 3, negative 3x plus 3, subtract over the 3 to get a 1, divide by negative 3, x can't be equal to negative 1/3. So what that's telling me is that not only can't x be equal to 1, because that will make the g function undefined, but x can't be equal to negative 1/3, because if I put negative 1/3 into the g function, that's going to create a number, negative 3, that's going to create this f function to be undefined. So I have two domain restrictions. Notice that it changed. It changed because this is when the g of x is going to create the negative 3, and I want to know what x coordinate will create the negative 3 once I put it into the g function. Okay? Now, some people like to find the domain of f of g in a different approach. It's more work, but it also works. So some people will say, well, let's go find f of g of x. Let's go see what this whole entire fractional expression is going to look like. Okay, so let's take the 4 over x minus 1, and you're going to plug it in for x into the f function. So I'm taking 4 over x minus 1, and I'm going to plug it into that x position right there. Now, this isn't too bad because there's only one x you have to substitute in. However, if my f of x function was a fraction that had an x squared plus x plus 1 on the top and an x plus 3 on the bottom, okay, this would be a lot of work because that's a lot of substitutions, a lot of simplifying with fractions. But this isn't too bad. So now that I plugged it in for the x in the denominator of the f, we need to turn this into one denominator on the bottom. So I'm going to take the 3 and multiply top and bottom by x minus 1 so I can make this into one fraction. So I'm going to get 4 plus 3x minus 3 on the bottom. The 4 and the minus 3 combine to be a plus 1. Okay, now because it's 1 over this fraction, well, we don't divide by fractions. We multiply by its reciprocal. So x minus 1 over 3x plus 1 multiplied by 1 is no change. So here's my answer. Now, notice that if you were to take this denominator, 3x plus 1, take that denominator 3x plus 1, solve it for x would equal the negative 1/3. And that's where you find that new value. Now remember, because g is the inner function, that inner function's domain restriction automatically goes with the answer, even though the x minus 1 appears on the top at the end. But look at where we started at right here. X minus 1 is in the denominator of the bottom fraction. That will cause an undefined value in the denominator here. And then the bigger fraction, 3x plus 1, well, if x equals negative 1/3, that turns this fraction on the bottom into a 0, and then the big fraction becomes undefined. So that's another way to find your domain. If you were asked to find g of f of negative 4, they're going to give you values. So this is a true double substitution. F is the inner function, g is the outer function, so we're going to evaluate f of negative 4 first. So we're going to take negative 4, put it into the x location of the f function. That's 1 over negative 4 plus 3. So notice, just as if you were simplifying, you got to simplify the inner parentheses first, and once you have this number, then you can use it with the outer function. So negative 4 plus 3 is negative 1. So that's going to be g of negative 1. 1 over negative 1 gives me negative 1. Now that the inner function has been completely simplified, now we take negative 1 and put it into the x of the g function. And negative 1 minus 1 is going to be negative 2. So 4 over negative 2, or negative 4 halves, that's equal to negative 2. All right? Make sure you practice these fractions with these domain restrictions. This author is big into finding the domain. Okay, better examples if we just have nice polynomial functions. So here we're going to plug in some numbers here. So again, double substitution. This is h of j of 1. Again, I like to write it this way. I'm going to go take j of 1, plug 1 into the j function. 4 times 1 is going to be 4. And so now I have to find h of 4. Take the 4 and plug it into the h function. 4 squared is 16, times 2 is 32, minus 3 is 29. That's my final answer. H of j of 1 is equal to 29. All right, B, j of h of 1. Notice I switched the order of the functions. The reason I did that is let's see if we get the same answer. So this is j of h of 1. So now 1 goes into the h function first. So 1 squared is 1, times 2 is 2, minus 3 will be negative 1. Then we take the negative 1, we put it into the j function. 4 times negative 1 is negative 4. All right, wait a minute, we didn't get the same answer. And you should. That would only account for a very special case, which we'll talk about in a bit. You can even have a function inside of itself. And in fact, you can do 3 or 4. You can go h of h of h. You can go j of h of j of h. You can have as many of these nested functions as you want. So we'll take h of negative 2, take the negative 2, plug it into the h function, simplify this. All right, negative 2 squared is 4. 4 times 2 is 8. 8 minus 3 is going to give me a 5. Now we take that 5 and you repeat. You go back and you put it into the h function again. 2 times 5 squared. Okay, 5 squared is 25. Times 2 is 50. Then 50 minus 3 is 47. So h of negative 2 is 47. If we do j of negative 1, I like this one here because if you get functions that are real small like this, you can challenge yourself and see if you can do this between your ears. Okay, so let's see. Negative 1 goes in here, so that's negative 1 times 4 is negative 4. Then I got to put negative 4 back into the same thing. 4 times negative 4. Negative 16. So let's see if we're right. So there's the negative 4. Yep, negative 4 goes back in. Yep, there's negative 16. So when you have some of these small, short functions, you challenge yourself. See if you can get that done between your ears. So j of negative 1 is equal to negative 16. Now, if, in example E, they do not give you a value, they leave an x here, then your answer has to be a variable expression in terms of x. Just like we talked about earlier in chapter 3. If they put a 1 in for x, you're going to end up with a number for an answer. All right, if they give us an x to start with, then x's has to be in our answer. So this becomes h of j of x. So here, you really don't have to simplify anything with j of x. You just take this whole entire 4x, and you're going to plug it into every x of the h function. Well, in this case, there's only one x. So that becomes 2 times the 4x squared. So let's square that first. So that becomes 16x squared. And then multiply it to the 2, which makes it 32x squared minus 3. So there's my answer. If I start with x, x is left over in my answer. And if we switch the functions around, just like we saw with the numbers, you better not get the same answer. So j of h of x, so that means now the entire h function, 2x squared minus 3, is going to go into the x of the j function. So that's just going to be 4 times that 2x squared minus 3, okay, 8x squared minus 12. And as you can see, these two expressions are not the same. Now, we can also do these composition functions with tables. Now, sometimes this confuses people, but just let me point this out here. The top row represents your x coordinates. That's the value that's going into the function. The row that says f of x and g of x, these are the outputs. These are the y coordinates. So if I put negative 3 into the f function, I get a negative 4. If I put negative 3 into the g function, my y coordinate's 9. All right? So if we're trying to find f of g of 2, then I'm going to rewrite this as f of g of 2. I'm going to go find g of 2 first. So we're going to go up and find the x. That's 2. There it is, right here. And then I'm going to go down to the g row and return the answer of 3 on the inside of the parentheses, not the whole answer. So now I have to find f of 3. So now that 3 becomes my x coordinate. So now I'm going to go up to the 3 at the x coordinate and then go down to the f function and return the 4. All right? So just to show you that again, take that 3. You're then going to go up to the x. And then you take that 3 and go to the 4, and that's your answer, because 4 is in the f row. All right, g of f of negative 1. All right, so negative 1, start there. Negative 1 to the f function is negative 2, so that's g of negative 2. Then we go to -2, and we go down to the g function, and that gives me a 3. All right, try the third one on your own. G of -2. So if you want to pause the video, pause it. Okay, welcome back. So -2 to the g function gives you a 3. Then you go back over to this 3, down to the g row, and get a 9. Now there are cases, f of g of 3, where we do g of 3 first. Well, we just did g of 3. It's a 9. It's right here. So instead of going back up there, I'm just going to steal that. So that 9 goes in place of g of 3. And to do f of 9, and this can happen with tables, look, there's no 9s in the x row. So therefore, this is an undefined value. Nothing is returned. That can happen. So watch your directions. See if you have to put in undefined, or sometimes you have to put in DNE for does not exist. So make sure you pay attention to the directions. All right, our last couple examples here for 6.1. This is where now they're going to give you what f of g is equal to. So they say it's equal to capital H, and they give us capital H. They want you to find the two individual functions. Okay, well, based on the notation f of g, g of x is the inner function. Now here's how I always do these problems. G of x is inside parentheses. Which function is inside parentheses or a grouping function? So we said g of x is in the parentheses. Who's in my grouping symbol? X cubed plus 5 is inside the grouping symbol of a square root. Okay, that's your g of x. Now, if I take out the x cubed plus 5, then I'm left with an empty square root. Well, that's got to be my f function. That's my f of x. So we take out the x cubed plus 5, replace it with an x, and that's your f of x function. So if you took x cubed plus 5 and replace that x, you get h. You can also find another possible pair. So there's usually never one correct answer. The exponents are considered to be a grouping symbol. Okay, so we could say g of x is equal to x cubed. Take out the x cubed, and then put in an x, and you have the square root of x plus 5. That's another possibility. I like this one here because there's always a grouping symbol somewhere. Radicals, parentheses, absolute value bars, there's something there. Okay, so if we try the last one, f of g is equal to h. So again, g of x is the inner function. I see inside parentheses my g of x, that's my inner function. So therefore, inside my parentheses is an x squared plus 1. That's going to be my g of x function. Take out the x squared plus 1, throw an x back in. Well, you could leave it as parentheses with an x in it raised to the 5th power, or just write it as x to the 5th. That works as well. And then again, your second option, just like we said with x cubed could be your inner function, x squared could be your inner function. Take out the x squared, replace it with an x, and then x plus 1 to the 5th power could be your outer function. Both of them work. The only reason I don't like this one right here is because sometimes you don't have some x raised to a power. And if that's what you're looking for, then you don't find your inner function. I always go with the grouping symbols. Okay? All right, so that ends 6.1.